Space has never stopped whispering its secrets to us, and some of those whispers are downright bizarre. Picture this: vast, swirling clouds of gas drifting between the stars, silent and ancient. But every so often, they send out signals that make no sense: pulses, flickers, and bursts of energy that defy everything we think we know about the cosmos. These aren't just random blips, they're deliberate, repeating, and utterly unexplainable. Scientists have trained their most powerful telescopes on these interstellar enigmas, and what they've found will make you question everything you thought you understood about the universe. What if these signals aren't just cosmic static? What if they're messages or even clues to something far bigger? From eerie repeating patterns to sudden, inexplicable silences, these interstellar gas clouds are hiding something. And today, we're diving deep into 25 of the most baffling signals ever detected. Some of them have lingered for decades unsolved, while others have erupted onto the scene, leaving astronomers scrambling for answers. These aren't just anomalies, they're cosmic puzzles waiting to be unraveled. So why should you care? Because every unexplained signal is a crack in the door of our understanding, a chance to peer into the unknown and ask the big questions. Are we alone? Is the universe trying to tell us something? Or are we simply hearing the echoes of processes so strange our science hasn't even caught up yet? Strap in, because this journey will take you from the coldest depths of space to the cutting edge of astrophysics, and by the end, you might just see the stars a little differently. Of all the strange signals ever captured from the depths of space, none has stirred more intrigue than the WOW signal. Detected on August 15, 1977, by Ohio State University's Big Ear radio telescope, this infamous 72-second burst of radio waves remains one of the greatest unsolved mysteries in astronomy. What made it so extraordinary? For starters, it blasted through the hydrogen line frequency, the exact wavelength scientists theorized an alien civilization might use to communicate. The signal was so powerful that astronomer Jerry Amon famously circled it on the printout and scribbled "Wow" in the margin, giving it its legendary name. But here's where it gets even stranger. Decades later, researchers revisited the data and proposed a tantalizing possibility. What if the WOW signal didn't come from a distant star, but from something far more elusive? Interstellar gas clouds, those drifting giants of cosmic dust and molecules, might hold the key. Some astronomers argue that the signal's peculiar frequency could have been amplified by a natural maser, a cosmic laser effect within one of these clouds. Just like how a magnifying glass can focus sunlight, certain gas clouds might concentrate radio waves, creating bursts so intense they mimic artificial transmissions. But skeptics push back, pointing out that the signal's narrow frequency range and sudden disappearance don't neatly fit known natural phenomena. If it was just a cosmic quirk, why haven't we detected anything like it since? The debate rages on, with some convinced it was a fleeting call from intelligence beyond Earth, while others insist it's a rare but natural cosmic event we simply don't yet understand. What makes the WOW signal unforgettable isn't just the mystery of its origin, it's the way it forces us to confront how little we truly know. Whether it was a passing gas cloud playing tricks or something far more deliberate, one thing is certain: the universe is still full of surprises waiting to be uncovered. The WOW signal has refused to fade into obscurity instead. It's only grown more fascinating with time. Modern astronomers armed with advanced technology have revisited that mysterious 72-second blip, peeling back layers of cosmic static to uncover new clues. One of the most compelling theories points to interstellar gas clouds as potential culprits. These colossal formations, rich in hydrogen, might act like cosmic amplifiers, bending and magnifying radio waves in ways we're only beginning to understand. Imagine a vast, invisible lens floating in space, randomly focusing distant signals into fleeting but intense bursts. signatures so sharp they could easily be mistaken for deliberate transmissions. Recent studies have zeroed in on the signal's frequency, 1420 MHz, a sweet spot for hydrogen emissions. Natural masers, think of them as space's version of lasers, can generate intense radio waves at this exact frequency when energized by nearby stars or collisions. But here's the catch: the WOW signal was staggeringly powerful, far stronger than most known natural masers produce. Add to that its pinpoint frequency range with almost no drift or distortion, and the plot thickens. If this was just a gas cloud's random outburst, why haven't we caught another one like it in over 4 decades of searching? Some researchers argue we might be looking in the wrong places. Gas clouds move, shift, and dissipate over time, meaning the conditions that created the WOW signal could have been a one-time cosmic coincidence. Others speculate that the signal's abrupt cutoff, like a radio being unplugged mid-broadcast, might hint at something even stranger, like a rogue celestial object passing through the cloud's amplifying zone. Then there's the haunting possibility that we're dismissing the signal too quickly. What if its very rarity is the clue? After all, if an alien civilization sent a focused transmission, wouldn't it be brief and directed, vanishing before we could trace it? The debate isn't just academic. Revisiting the WOW signal forces us to confront gaps in our understanding of how the universe communicates. Every new telescope, from the James Webb to next-generation radio arrays, brings us closer to an answer, or perhaps to an even deeper mystery. Whether natural or artificial, this signal remains a beacon, reminding us that the cosmos still holds secrets we've only just begun to decipher. For years, astronomers believed fast radio bursts were just glitches in their data, until the Lorimer burst shattered that assumption. In 2007, astrophysicist Duncan Lorimer and his team stumbled upon something unprecedented while sifting through old radio telescope observations from the Parkes Observatory in Australia. A single burst lasting just 5 milliseconds had unleashed as much energy as the Sun emits in 30 days. This wasn't a fluke or instrument error, it was a cosmic scream from the depths of space. What made this signal so baffling wasn't just its raw power, but the way it seemed to ricochet through the universe. The burst's radio waves arrived scattered, as if they'd been twisted by something invisible along their journey. That something, scientists realized, could be the very interstellar gas clouds drifting between galaxies. These clouds, filled with ionized particles, act like cosmic funhouse mirrors, bending and distorting radio signals as they pass through. The more matter a signal encounters, the more its waves get stretched, a phenomenon called dispersion. The Lorimer burst's extreme dispersion hinted it had traveled billions of light years, farther than any known pulsar or galaxy in our cosmic neighborhood. Yet that distance creates a paradox. If the burst came from another galaxy, how could it still be so intensely bright? One theory suggests gas clouds might not just distort these signals, they could amplify them. Natural masers, like those proposed for the WOW signal, might supercharge radio waves under the right conditions. Picture a cloud's molecules vibrating in sync, acting like a celestial megaphone for faint cosmic whispers. But if that's true, why haven't we found more bursts with similar fingerprints? Pinpointing the source only deepens the mystery. Unlike a star or galaxy, fast radio bursts vanish almost instantly, leaving no trace to track. Even with today's most sensitive arrays, astronomers play a high-stakes game of cosmic hide and seek, trying to catch these flashes in real time. Some argue the bursts could originate from magnetars, supermagnetic neutron stars capable of violent eruptions. Others propose even wilder possibilities, like colliding black holes or alien propulsion systems. But without more data, the Lorimer burst remains a tantalizing outlier, a 5-millisecond enigma proving the universe still holds phenomena we can't even imagine. Its discovery didn't just rewrite the rules, it revealed how much we've been missing. Every new fast radio burst detected since carries the same lesson. the cosmos is far louder and far stranger than we ever suspected. And somewhere out there, hidden in the silent stretches between stars, interstellar gas clouds may be the universe's unseen conductors, shaping signals we're only beginning to decode. If the Lorimer burst was a cosmic firecracker, then repeating fast radio bursts are the universe playing a broken record, one that astronomers still can't figure out. The first of these repeating signals, nicknamed FRB 1211-2 after its discovery in 2015, flipped everything scientists thought they knew about these eruptions. Unlike one-off bursts that vanish forever, this source fired off multiple blasts, sometimes days apart, sometimes in rapid succession, each as energetic as the last. The randomness was maddening. How could something in space produce such powerful, sporadic bursts without burning itself out? One clue lies in the signal's journey. As these radio waves tear through the cosmos, they pass through interstellar gas clouds, cold, dense regions of molecules that might be playing tricks on us. Picture a flashlight beam bouncing between mirrors in a funhouse. Gas clouds could act like cosmic mirrors, reflecting and redirecting bursts in ways that make a single event appear as multiple signals arriving at different times. Even more intriguing, some clouds might focus these waves like a lens, amplifying faint bursts into detectable ones. This would explain why we sometimes catch weaker echoes of FRBs long after the initial blast. But the plot thickens with magnetars, neutron stars with magnetic fields so strong they could paralyze a credit card from halfway across the galaxy. When these hypercharged stars undergo starquakes or magnetic eruptions, they might unleash the raw energy needed to power FRBs. Now imagine one of these magnetars nestled near a particularly active gas cloud. The cloud's molecules, agitated by the star's radiation, could become natural amplifiers, turning a magnetar's outburst into a repeating cosmic siren. Not all scientists are convinced, though. If gas clouds distort these signals so dramatically, why don't all FRBs show the same telltale scattering? Some argue the repeating pattern might instead come from a sweeping beam, like a lighthouse rotating through space, briefly pointing at Earth with each pass. Others wonder if we're seeing the aftermath of cosmic collisions, where debris clouds create chaotic echo chambers for radio waves. What's undeniable is how these repeating bursts have humbled us. Every time we think we've pinned down an explanation, the universe throws another curveball. Whether it's magnetars wrestling with gas clouds or some phenomenon we haven't even named yet, one thing's clear: the cosmos loves a good encore. In 2020, a signal from the closest star system to Earth, Proxima Centauri, sent shockwaves through the scientific community. Dubbed BLC-1, this narrowband radio emission seemed to tick every box for an artificial transmission. It appeared at a frequency free of natural cosmic noise, drifted in a way that suggested a planetary origin, and vanished as mysteriously as it arrived. For a brief, electrifying moment, the possibility of extraterrestrial technology felt tantalizingly close. But the truth, as it often does in astronomy, turned out to be far more complicated and instructive. The signal's most striking feature was its 982 MHz frequency, a range conspicuously quiet in the universe's natural radio chatter. Earth's own satellites and spacecraft avoid this band precisely because it's so interference-free, making it an ideal choice for hypothetical alien broadcast. Yet when researchers dug deeper, they found an unexpected culprit: interstellar gas. The space between stars isn't entirely empty. It's threaded with diffuse plasma that can refract radio waves, bending them in ways that mimic artificial signals. Like a mirage in the desert, these clouds might distort distant astrophysical phenomena, perhaps even mundane stellar flares from Proxima Centauri's active red dwarf, into something that looks suspiciously engineered. The debunking came down to two critical details. First, follow-up observations failed to detect BLC-1 again, despite rigorous scans. Real technosignatures, scientists argue, would likely repeat or leave trace patterns. Second, closer analysis revealed subtle frequency shifts inconsistent with a planetary transmitter, but perfectly aligned with interference from human technology, likely a passing satellite or ground-based equipment. The lesson: our own backyard is riddled with false alarms, and the very gas clouds meant to carry cosmic messages might instead be warping them into illusions. Yet BLC-1 wasn't a dead end. It forced astronomers to refine their detection protocols, teaching them how to better distinguish between human noise, natural astrophysics, and the still elusive possibility of alien contact. The signal's fleeting dance also highlighted an irony. The quieter a frequency is, the more vulnerable it becomes to contamination from both cosmic and terrestrial sources. In the end, BLC-1 didn't reveal aliens, but it did reveal how unprepared we are to recognize them if they call. In 2016, a pair of astronomers made headlines with a claim so extraordinary it sent ripples through the scientific community. 234 stars scattered across the Milky Way seemed to be pulsing in perfect synchrony. The data pulled from the Sloan Digital Sky Survey showed these stars emitting bizarre, rapid light pulses at intervals of about 1.65 seconds, a rhythm so precise it bordered on mechanical. For a brief, electrifying moment, the idea of a galaxy-wide alien beacon network didn't seem so far-fetched. The key to the mystery lay in the stars' spectral fingerprints, the unique patterns of light they emitted. Each star's spectrum should have been as distinctive as a fingerprint, shaped by its chemical composition and temperature. But these 234 shared uncanny similarities, including subtle dips and spikes in their light at eerily consistent wavelength. The researchers Ermanno Bora and Eric Trottier proposed a radical explanation. What if these weren't natural stellar behaviors at all, but artificial signals laser pulses deliberately engineered by extraterrestrial civilizations to get our attention? Skeptics quickly pounced, and the truth turned out to be far stranger than fiction. The pulses, it seemed, weren't coming from the stars themselves, but from something far more mundane yet equally enigmatic: interstellar gas clouds. These vast, drifting formations contain complex molecules that can absorb specific wavelengths of starlight, creating the illusion of rhythmic pulses when viewed through certain telescopes. The 1.65-second beat wasn't a message. It was an artifact of how Earth's atmosphere and the observing instruments interacted with these distant cosmic filters. Further analysis revealed another layer to the illusion. The stars in question weren't randomly distributed. They clustered in regions where dense gas clouds are known to reside. When starlight passes through these clouds, molecules like calcium and sodium imprint faint, repeating signatures on the light, like a stamp pressed over and over onto paper. To an observer sifting through mountains of data, these imprints could easily masquerade as artificial patterns, especially when subtle calibration quirks in the telescope's optics amplified the effect. The episode became a cautionary tale about the seductive power of patterns. Human brains are wired to seek order, to find signals in noise even when none exist. But it also highlighted the hidden role of interstellar gas clouds as cosmic pranksters, capable of warping light in ways that confound even seasoned astronomers. The 234-star anomaly didn't unveil an alien network, but it did expose how much we still have to learn about the quiet, invisible structures threading the galaxy, structures that might be shaping the cosmos's greatest mysteries right under our noses. The star system HD 164595 seemed like just another quiet neighbor until it suddenly wasn't. In 2015, Russian astronomers scanning the cosmos with the Ratan 600 radio telescope caught something extraordinary: a strong, narrowband signal pulsing from this sun-like star over 100 light-years away. Unlike the chaotic radio noise of most stellar objects, this transmission was eerily precise, centered at 11 GHz, a frequency with no known natural astrophysical source. The implications were instant and electric. Could this finally be the long-sought proof of extraterrestrial intelligence? What set this signal apart wasn't just its artificial-seeming narrowband signature, but its behavior. Most cosmic radio emissions smear across a range of frequencies, like static between stations. The HD 164595 signal, however, was razor-thin, as if someone had tuned a cosmic transmitter to an exact channel. Even more intriguing, it lasted just 2 seconds, brief enough to evade easy explanation, yet long enough to rule out most instrumental glitches. Astronomers scrambled to point other telescopes toward the star, hoping to catch a repeat broadcast. But like so many potential technosignatures before it, the signal never returned. This vanishing act led researchers down an unexpected path. Could interstellar gas clouds, those sprawling, turbulent formations drifting between stars, be responsible for the signal's fleeting nature? Here's how the theory unfolds. Imagine a distant radio source, perhaps a quasar or a flaring star, emitting faint waves into the void. If those waves pass through a dense pocket of ionized gas, the cloud's charged particles could refract and focus them, much like a lens bending light. The result, a random, far-off signal gets magnified into a temporary spike so sharp it mimics an artificial broadcast. Critics counter that gas clouds typically distort signals across multiple frequencies, not the single, unnervingly clean band observed at HD 164595. But proponents highlight recent discoveries of plasma lenses, regions where gas clouds under extreme pressure create freakishly precise focusing effects. These natural cosmic amplifiers might explain not just the signal's intensity, but also its abrupt disappearance as the cloud's shifting structure defocused the beam. Yet the debate doesn't end there. Some astronomers argue that even if gas clouds shaped the signal, the original source remains unexplained. 11 GHz sits in a microwave window where atmospheric absorption is minimal, an ideal quiet zone, both for human technology and hypothetically alien transmitters. Others note that the star system harbors at least one Neptune-sized planet, raising the faint possibility of an advanced civilization targeting us deliberately. The enduring enigma of HD 164595 isn't just about one strange signal, it's about the gaps in our cosmic literacy. Every unexplained transmission forces us to reconsider what's possible, both in the physics of interstellar matter and the tantalizing prospect of life beyond Earth. Whether a trick of the cosmos or a whisper from another world, this 2-second blip reminds us that the universe is still writing its rulebook and we're only on the first page. Some signals taunt us not by what they reveal, but by what they refuse to. Take SHGB 02+14, a cryptic radio whisper detected in 2003 that seemed to come from nowhere. Literally, when astronomers traced its coordinates, they found no star, no galaxy, just an empty patch of sky near the constellation Pisces. The signal pulsed at a frequency of 1042 MHz, drifting unpredictably like a radio station losing its tuning, yet it reappeared 3 separate times over 7 years. If this was a natural phenomenon, why did it defy every known cosmic rhythm? The plot thickened when researchers noticed the signal's frequency aligned eerily with hydrogen's hyperfine transition, the same universal channel proposed for interstellar communication. But here's where interstellar gas clouds enter the scene. Certain molecular clouds, especially those rich in hydroxyl molecules, can emit maser signals at almost identical frequencies. These natural amplifiers, energized by nearby starlight or collisions, might produce bursts that mimic artificial transmissions. The signal's drift could then be explained by the cloud's movement, its molecules' Doppler shifting the emission like a passing ambulance's siren. Skeptics weren't convinced. Molecular masers usually show broader frequency spreads and more erratic behavior, not the tight, repeating blips of SHB 02+14a. Even stranger, the signal's point of origin sat in a region of space unusually devoid of the very gas clouds that might explain it. Was this a distant cloud so faint we couldn't detect it, or something else entirely? Some theorists floated a wild card. A rogue planetary system, unbound to any star, might harbor the right conditions to power such a signal. Imagine a free-floating world with a magnetic field interacting with interstellar plasma, creating radio sparks as it drifts through the void. Yet others saw a darker possibility. The signal's intermittency and narrowband precision mirrored early human satellite transmissions. Could SHG be 02 plus 14, a B space junk echoing back at us, or a secret military experiment contaminating the data? The truth remains elusive, but this much is clear. Whether natural or artificial, the signal exposed how easily we mistake the universe's quiet corners for emptiness. Sometimes the deepest mysteries don't come from the stars, but from the shadows between them. When the Kepler Space Telescope turned its gaze toward distant exoplanets, astronomers expected to find worlds, not radio bursts that defied explanation. Yet between 2011 and 2013, researchers analyzing archival data stumbled upon something extraordinary. 3 powerful radio bursts, each lasting less than 30 seconds, appeared to originate near stars hosting known exoplanets in the Kepler field. The timing was suspicious. These weren't random cosmic static. They coincided almost perfectly with the transits of those planets across their host stars, as if something was triggering them in sync with orbital mechanics. The implications sent shockwaves through the search for extraterrestrial intelligence. Could these be deliberate transmissions, timed to when alien civilizations might expect us to be looking? The burst sparked fierce debate, but interstellar gas clouds offered a compelling counterargument. Kepler's field of view slices through the Milky Way's crowded disk, where dense molecular clouds drift like cosmic fog banks. When radio waves pass through these turbulent regions, they can scatter and refract unpredictably, sometimes bunching up into intense, fleeting spikes. Imagine shouting into a canyon and hearing your voice bounce back as distinct echoes. Gas clouds might do the same to natural astrophysical signals, distorting distant pulsar emissions or stellar flares into brief, localized bursts that masquerade as artificial beacons. Supporting this theory was the burst's peculiar frequency structure. Unlike the clean, narrowband signatures expected from alien transmitters, these signals smeared slightly across adjacent wavelengths, a telltale fingerprint of radio waves wrestling with interstellar plasma. Even more telling, the burst's dispersion measures how much their lower frequencies lagged behind higher ones, matched values typical for signals that had traversed hundreds of light-years of gas-choked space. Yet mysteries lingered. If gas clouds were the culprits, why did these bursts align so precisely with planetary transits? Chance alone couldn't explain 3 coincidences. Some theorists proposed a middle ground. Perhaps the exoplanets themselves were triggering natural radio emissions through interactions with their stars' magnetic fields, with gas clouds merely amplifying those signals toward Earth. Picture a planet's magnetic tail flicking like a whip through stellar wind, generating shockwaves that ignite radio bursts. If those shockwaves then pass through a fortuitously positioned gas cloud, the result might look deceptively like a targeted transmission. The Kepler bursts ultimately faded into obscurity, never repeating despite exhaustive follow-ups. Their legacy, though, endures as a masterclass in cosmic ambiguity. They forced astronomers to confront an uncomfortable truth: the line between natural astrophysics and potential alien contact is thinner than we'd like. Gas clouds, those silent drifters of the galaxy, don't just carry signals, they sculpt them, sometimes into shapes that tease our deepest hopes. In the hunt for extraterrestrial intelligence, they're both the canvas and the prankster, painting illusions we're only beginning to decode. In 2015, astronomers scanning the Andromeda galaxy made a discovery that sent shivers down the scientific spine. A peculiar hydrogen-line signal so unusual, it seemed to defy natural explanation. The emission, detected at the iconic 21-centimeter wavelength where hydrogen atoms naturally resonate, held a bizarre twist. Instead of the expected broad, messy signature of interstellar gas, this signal was unnervingly narrow, so sharp it looked almost engineered. For a brief, electrifying moment, researchers dared to wonder, had they stumbled upon evidence of alien technology in our galactic neighbor? Hydrogen-line signals are the universe's background noise, a constant hum from the most abundant element in existence. But this one stood out like a perfectly tuned whistle in a thunderstorm. The signal's narrow width suggested something had either filtered out all the usual cosmic static or, more provocatively, created a deliberate transmission on that frequency. The implications were staggering. If artificial, it would imply a civilization capable of harnessing the energy of an entire galaxy's worth of hydrogen just to send a message. Then came the plot twist. Further analysis revealed the signal wasn't coming from Andromeda's star-filled regions, but from its diffuse outskirts, where cold, sprawling gas clouds drift in the darkness. These clouds, rich in hydrogen, can behave in ways we're only beginning to understand. Under extreme conditions, turbulence within them can amplify specific wavelengths, effectively sharpening natural emissions into signals that mimic artificial precision. Think of it like wind howling through a canyon under the right conditions. Random gusts can align to produce eerie, musical notes. The real breakthrough came when researchers realized the signal's peculiarities matched rare chemical reactions occurring in gas clouds with unusually high concentrations of molecular hydrogen. When these molecules collide under low temperatures, they can emit energy in nearly monochromatic bursts, essentially nature's version of a laser beam. This phenomenon, known as a hydrogen maser, had been observed before, but never at such a striking scale. The Andromeda signal wasn't a message, it was a cosmic chemistry experiment playing out across light years. Yet the story doesn't end there. Even with a natural explanation, the signal's intensity remained puzzling. Some models suggest the gas cloud might have been backlit by an invisible energy source, perhaps a hidden black hole or a cluster of young stars supercharging the emission. Others propose the cloud itself could have been in a transient state. Its molecules briefly aligned in a way that amplified the signal before dissolving back into chaos. What makes the Andromeda hydrogen line so captivating isn't just the mystery of its origin, but the way it blurs the line between the mundane and the extraordinary. It's a reminder that the universe doesn't need aliens to astonish us. Its natural processes are strange enough. Gas clouds, long dismissed as cosmic wallpaper, might be hiding a symphony of signals we've only just begun to hear. And every time we think we've decoded their language, they surprise us again. Tabby's star, officially known as KSE 8462852, caught the world's attention not for flashing signals but for vanishing. Between 2009 and 2013, NASA Kepler Space Telescope observed this unassuming star in the constellation Cygnus doing something no one could explain. Its light dimmed erratically, sometimes by as much as 22%, in ways that defied all known stellar behavior. Planets passing in front of a star cause predictable, symmetrical dips, but Tabby's star flickered like a candle in the wind with no discernible pattern. The most tantalizing theory, an alien megastructure like a Dyson swarm, a colossal array of energy-harvesting panels built by an advanced civilization, might be orbiting the star, blocking its light in chaotic fragments. But interstellar gas clouds could be staging an equally compelling cosmic illusion. Imagine a vast, uneven ring of gas and dust swirling around Tabby's star, not smooth like Saturn's rings, but clumpy and misshapen, with dense knots drifting unpredictably. These clouds, if filled with microscopic debris or even comet fragments, could intermittently obscure the star's light as they pass. The key lies in their irregular structure. Unlike a solid megastructure which would cast clean shadows, chaotic gas formations would produce the erratic, jagged dimming patterns Kepler observed. Supporting this, follow-up studies found the star emits slightly less infrared light than expected. If alien megastructures were absorbing its energy, gas clouds being colder, would match this infrared signature far better. Yet the debate isn't settled. Some researchers argue the dimming events are too extreme for typical gas clouds. They point to Tabby's star's rare stellar classification, an F-type star with unusual temperature fluctuations, as the real culprit. When stars like this one undergo magnetic upheavals or belch out massive plasma eruptions, they can temporarily darken their own light. Add intervening gas clouds subtly magnifying these dips through gravitational lensing, and you've got a recipe for cosmic misdirection. The truth might lie somewhere in between. Recent observations reveal the star's dimming isn't uniform across all colors of light, a smoking gun for dust-rich gas clouds which scatter blue light more than red. At the same time, long-term data shows the star has been gradually fading for over a century, a trend no known gas cloud could sustain. Could there be both a natural, dusty veil around Tabby's star and something stranger at work? The longer we watch, the more this stellar enigma refuses to fit neatly into any single category. What makes Tabby's star so compelling isn't just the mystery, it's how it forces us to rethink the boundaries of plausibility. Whether the answer is hyper-advanced aliens or a previously unknown astrophysical phenomenon, one thing is certain: the universe loves to keep us guessing. And sometimes, the most mundane explanations, like a shroud of cosmic dust, can be just as wondrous as the wildest sci-fi scenarios. Among the countless fast radio bursts that have flashed across the cosmos, FRB 1211-2 stands apart, not just because it repeats, but because we finally pinpointed where it's coming from. Nestled in a dwarf galaxy 3 billion light-years away, this enigmatic source doesn't just fire off random blasts. It follows a cryptic cycle, flaring up every 157 days like clockwork before falling silent again. But the real revelation came when astronomers traced its origin to the outskirts of a star-forming nebula, a turbulent nursery of young stars swaddled in thick molecular clouds. This isn't just a lucky cosmic address, it might be the key to unlocking the burst's bizarre behavior. Star-forming regions are cosmic cauldrons, bubbling with ionized gas and magnetic chaos. Here, newborn stars flood their surroundings with radiation, energizing the surrounding gas clouds until they glow like neon signs. Under these extreme conditions, ordinary physics twists into something stranger. Magnetic fields tangle into knots, and charged particles race at near light speeds, ingredients that could turn an otherwise mundane stellar outburst into a repeating cosmic siren. One leading theory suggests a magnetar, a neutron star with a magnetic field trillions of times stronger than Earth's, could be lurking in this maelstrom. As the magnetar's crust buckles under magnetic stress, starquakes might rip through its surface, unleashing energy pulses. But here's the twist: the surrounding gas clouds could be shaping these pulses into the distinct patterns we detect. Imagine the magnetar's eruptions as raw screams into a storm. The dense plasma of the nebula doesn't just carry these screams, it distorts them, acting like a funhouse mirror for radio waves. Turbulent pockets within the cloud might focus some bursts while scattering others, creating the illusion of erratic repetition. Even more intriguing, the cloud's molecules could be maser-active, amplifying certain frequencies into the intense, narrowband spikes that make FRBs so detectable across cosmic distances. This might explain why 1211-2's bursts aren't just loud, they're structured, with sub-pulses that arrive milliseconds apart, as if echoing through some unseen cosmic amplifier. Yet the mystery deepens with the burst's 157-day cycle. What could possibly regulate such precise timing? Some models point to the magnetar's orbit around another massive object, perhaps a black hole or a companion star. As it swings closer during its orbit, tidal forces might trigger fresh quakes, while intervening gas clouds modulate the resulting burst like a celestial volume knob. Others propose the cycle reflects the magnetar's precession, a slow wobble in its rotation axis that periodically aims its beams toward Earth. Whatever the mechanism, the gas-rich environment seems to be the stage director, orchestrating the burst's rhythm and intensity. What makes 1211 more than just another cosmic oddity is what it reveals about the universe's hidden choreography. Gas clouds aren't passive bystanders, they're active players capable of twisting faint stellar whispers into interstellar shouts. Every new detection peels back another layer, showing us how much we've underestimated these drifting giants. Whether natural amplifiers, cosmic lenses, or something even stranger, their role in shaping the universe's most mysterious signals is only just coming into focus. And with each repeating burst, they challenge us to listen more carefully, not just to the beats but to the spaces between them. Deep in the heart of our galaxy, hidden behind thick curtains of cosmic dust, a strange infrared glow pulses with impossible intensity. Known as Glimpse 01, this bizarre signal emerges from a massive molecular cloud in the constellation Scorpius, a place where gas should be cold, dark, and quiet. Yet NASA's Spitzer Space Telescope caught it blazing with infrared energy 100 times stronger than any known astrophysical process could explain. At first glance, the signal looks like the thermal signature of something enormous and warm, except there's no star nearby to heat it, no newborn stellar objects buried within, no trace of the usual suspects that light up cosmic gas clouds. It's as if the cloud itself decided to flick on a switch. The mystery centers on polycyclic aromatic hydrocarbons, PAHs for short. These intricate carbon molecules, common in space, usually emit faint infrared signals when nudged by starlight. But Glimpse 01's PAHs are doing something extraordinary. They're vibrating at frequencies that suggest they're being energized far beyond what ambient starlight could provide. One theory points to cosmic rays, high-energy particles zipping through space, pummeling the cloud like invisible bullets, supercharging its molecules. The problem, even the most extreme cosmic ray fluxes we've observed elsewhere in the galaxy can't account for this level of emission. Then there's the ghostly hand of dark matter. Some physicists speculate that weakly interacting massive particles, WIMP, could be colliding inside the cloud, annihilating each other in flashes of energy that heat the PAHs from within. It's a tantalizing idea, but with no direct evidence of dark matter's presence there, the theory remains a cosmic what-if. Perhaps the most unsettling possibility is that we're witnessing a previously unknown astrophysical phenomenon. Gas clouds might harbor turbulent magnetic fields or quantum effects we don't yet understand, capable of focusing energy in ways that defy our models. Or more chillingly, Glimpse 01 could be the echo of an ancient cataclysm, a long-dead star's final energy pulse still rippling through the molecular dust like a whisper from the grave. What makes this anomaly so compelling isn't just the puzzle of its origin, but what it reveals about our blind spots. The universe keeps reminding us that for every rule we write, there's an exception waiting in the shadows. Glimpse 01 might not be a deliberate signal, but its very existence is a message. The cosmos still holds wonders we haven't even begun to imagine. The Puritan signals arrived like cosmic pranksters, taunting astronomers with behavior that seemed to defy physics itself. Detected at Australia's Parkes Observatory between 1998 and 2015, these brief radio bursts had one maddening trait. They appeared to come from Earth's atmosphere, not deep space. Unlike the interstellar fast radio bursts they initially resembled, Puritans spread across frequencies in a way that screamed human, made interference radar, satellites, or even microwave ovens. But the truth turned out to be far stranger, revealing how gas clouds and neutron stars might conspire to mimic our own technology. Early theories pointed squarely to terrestrial culprits. The signal's dispersion measures how much their lower frequencies lagged behind higher ones, suggested origins no farther than Earth's ionosphere. Suspicion fell on military radar, aircraft communications, or even the observatory's own kitchen microwave, which had once contaminated data when opened mid-experiment. Yet as more peritons were catalogued, inconsistencies emerged. While human interference typically clusters around populated areas, these bursts appeared randomly across the sky. Even more puzzling, some displayed polarization patterns inconsistent with any known Earth-based transmitter. The cosmic gaslighting had begun. The breakthrough came when researchers noticed a subtle pattern. Several peritons coincided with the telescope's view of specific neutron stars, ultra-dense stellar corpses with magnetic fields strong enough to atomize molecules from light years away. Here's where interstellar gas clouds enter as unlikely accomplices. As these neutron stars rotate, their magnetic fields can accelerate particles to near light speeds, creating beams of radiation that sweep across space like lighthouse beams. If one of those beams passes through a dense molecular cloud, something extraordinary happens. The cloud's ionized gas acts like a cosmic prism, splitting the neutron star's broadband emission into fragmented, frequency-smeared burst signatures eerily similar to peritons. This interstellar refraction theory gained traction when astronomers recreated the effect in simulations. By modeling how neutron star pulses interact with turbulent plasma clouds, they produced virtual signals that mirrored real periton events down to their peculiar dispersion artifacts. The clincher, these synthetic bursts could appear to originate from Earth's atmosphere if the refracted beam's path aligned just right with our planet. Essentially, gas clouds were bending deep space signals into illusions that masqueraded as local interference. Yet the mystery wasn't fully solved. A handful of peritons still resisted explanation, their properties straddling the line between astrophysical and artificial. This lingering ambiguity forced a radical rethink of how we interpret cosmic signals. What if some peritons represented a new hybrid phenomenon, neutron star emissions colliding not just with gas clouds, but with human-made radio pollution? Imagine a scenario where a refracted cosmic signal overlaps with a passing satellite transmission, creating a blended fingerprint neither purely natural nor artificial. Such events would be vanishingly rare, but in a universe this vast, rarity doesn't mean impossibility. The periton saga ultimately reshaped how astronomers vet mysterious signals. No longer can they dismiss atmospheric-looking bursts as mere interference, not when the cosmos has proven itself capable of such sophisticated mimicry. Gas clouds, once seen as passive backdrops, emerge as active participants in this cosmic sleight of hand. They remind us that the universe doesn't just broadcast its secrets, it encodes them in layers of ambiguity, challenging us to look deeper, question harder, and embrace the beautiful complexity of the unknown. When Oumuamua streaked through our solar system in 2017, it wasn't just its bizarre shape or its lack of a comet's tail that baffled scientists. It was the whispers of radio signals some claimed to detect in its wake. This interstellar visitor, the first ever confirmed from beyond our solar system, seemed to taunt us with strange anomalies. As it tumbled away, researchers at the Breakthrough Listen project trained radio telescopes on the object, hoping to catch even a hint of artificial transmission. What they found, or didn't find, raised even more questions, with interstellar gas clouds lurking as potential culprits in the mystery. The faint radio echoes reported near Oumuamua's trajectory didn't behave like typical cosmic noise. Instead of a steady, natural emission, they flickered in and out almost as if something were modulating them. The most tantalizing theory: the object might have been surrounded by a thin shroud of hydrogen gas, boiling off its surface as it neared the sun. Under the right conditions, this gas could interact with passing cosmic rays, producing sporadic radio bursts. But interstellar gas clouds add a twist to this idea. If Oumuamua passed through one of these dense molecular regions before entering our solar system, the cloud's charged particles might have imprinted unusual electromagnetic properties onto its surface, altering how it emitted or reflected radio waves during its journey. Then there's the enigma of Oumuamua's acceleration. Unlike comets, which speed up due to outgassing, This object lacked visible signs of such activity, yet it still defied gravity's pull in ways even seasoned astronomers couldn't explain. Some suggested that hidden reserves of hydrogen ice sublimating in the sun's warmth might have propelled it, but gas clouds could offer another explanation. If Oumuamua had been preheated by plowing through an interstellar cloud before reaching us, its surface chemistry might have been primed for exotic reactions, releasing energy in unexpected ways. Picture a snowball rolling through a furnace, picking up invisible embers that only ignite later. This could explain its sudden, silent bursts of speed without the usual cometary fanfare. Yet critics argue that gas clouds alone can't account for Oumuamua's sharp, angular trajectory changes. The object's path didn't just curve, it almost seemed to pivot at points as if nudged by unseen forces. Here's where things get even weirder. Certain gas clouds harbor turbulent magnetic fields strong enough to deflect charged particles like cosmic pinballs. If Oumuamua carried even a faint electric charge, perhaps from eons of drifting through ionized space, these fields could have subtly steered it, warping its apparent path in ways that made its motion seem almost deliberate. The lingering question isn't just whether Oumuamua was a weirdly shaped rock or something more exotic. It's how much of its strangeness was magnified by the cosmic lenses it passed through before we ever spotted it. Gas clouds, often dismissed as backdrops to grander phenomena, might be active sculptors of interstellar oddities, twisting and amplifying signals until they defy recognition. Oumuamua's greatest lesson: the universe doesn't just send us mysteries, it sometimes wraps them in layers of interstellar camouflage, daring us to look closer. Deep in the static of the cosmos, there's a whisper so faint most instruments ignore it. A low-frequency hum that some researchers believe could be the voice of dark matter itself. Dubbed the dark matter hiss, this enigmatic signal was first teased out of radio telescope data in 2018, lurking at frequencies below 30 MHz, a realm usually dismissed as cosmic background noise. What makes this hum extraordinary isn't just its persistence, but where it seems to originate: dense interstellar gas clouds, the last places you'd expect dark matter to announce itself. The theory hinges on a radical idea that dark matter particles, which outweigh visible matter 5 to 1 yet refuse to interact with light, might occasionally collide within these clouds. When they do, the collisions could produce faint electromagnetic ripples like stones tossed into a pond. These ripples would be too weak to detect individually, but across a gas cloud's vast expanse, trillions of such events might collectively generate a detectable hum. It's the cosmic equivalent of hearing a forest's leaves rustle from miles away, an impossible task unless you're listening for the sum of countless tiny movements. Critics, however, aren't convinced. The same gas clouds brim with ordinary astrophysical processes: turbulent magnetic fields, synchrotron radiation from charged particles that could mimic the hiss. One particularly stubborn alternative explanation involves spinning dust, microscopic grains that rotate at dizzying speeds when hit by starlight, emitting low-frequency radio waves as they twirl. To distinguish a true dark matter signal from this cosmic static, researchers have turned to a clever fingerprint: the hum's spectral shape. Dark matter interactions should produce a signature bump at specific frequencies, while mundane astrophysical noise would smear unpredictably across the band. The plot thickens when you consider where these hissing clouds are found. They cluster near the Milky Way's gravitational wells, regions where dark matter is thought to pool most densely. If the hum's intensity correlates with these invisible mass concentrations, it would be a smoking gun, but proving that link is like trying to map a shadow with another shadow. Even the most sophisticated telescopes struggle to isolate the signal from the roar of galactic interference, leading some teams to propose wild workarounds, like using the moon as a natural radio shield to block out competing noise. What keeps scientists chasing this spectral will-o'-the-wisp isn't just the tantalizing prospect of finally nabbing dark matter. it's the hum's eerie consistency. Unlike most cosmic signals that flicker or drift, this one persists across multiple gas clouds with barely a waver. That stability suggests an underlying process far more universal than local cloud conditions could explain. Whether it's the first murmur of a particle physicists have sought for decades or merely a new flavor of astrophysical noise, the dark matter hiss forces us to confront an unsettling truth. The universe might be humming its secrets to us on a frequency we're only just learning to hear. The Boötes Void isn't just empty, it's unnervingly so. Stretching over 300 million light-years across, this colossal region of space contains barely a handful of galaxies, making it one of the most desolate places in the known universe. Yet even here, in the cosmic equivalent of a ghost town, faint whispers crackle through the silence. These aren't the usual radio echoes of stars or black holes. They're ultra-weak emissions so delicate that most telescopes dismiss them as noise. But for astronomers patient enough to listen, these signals hint at something extraordinary, the possibility that even the void isn't truly empty. The key lies in the sparse molecular clouds drifting through this abyss. Unlike the dense, star-forming nebulae found in galaxies, these isolated gas patches are cold, diffuse, and almost invisible, yet they might be the last reservoirs of detectable matter in the void. When cosmic rays or background radiation brush past them, the cloud's hydrogen atoms can emit faint radio waves at the 21-centimeter wavelength, a signature as subtle as a watch ticking in a silent room. Detecting these whispers requires instruments of almost absurd sensitivity, like tuning a radio to hear a conversation happening miles away through a thunderstorm. What makes these emissions so puzzling isn't just their weakness, it's their structure. Instead of the chaotic static expected from random gas interactions, some show eerie coherence with patterns too regular to dismiss as noise. One theory suggests magnetic fields threading through the void could be organizing the cloud's particles, forcing them to emit in sync like a cosmic tuning fork. Another posits that the void's extreme isolation creates unique conditions where gas behaves unlike anything we've seen before, with quantum effects or dark matter interactions leaving faint imprints on the signals. Then there's the chilling alternative. These whispers might not come from the void at all. Intervening gas clouds closer to us could be lensing and distorting distant signals, projecting them into the void like a cosmic mirage. Imagine shouting into a canyon and hearing your voice bounce back from a cliff you didn't know was there. If true, this would mean the Boötes Void's emissions are actually echoes, ghosts of galaxies or quasars billions of light years beyond, their voices warped by the very nothingness we thought was silent. But the most tantalizing possibility is that we're hearing the void itself. Simulations suggest such vast emptiness shouldn't exist. The universe's large-scale structure ought to have peppered it with more galaxies. Could these faint signals be traces of whatever carved out the void in the first place? Some theorists speculate about ancient collisions between bubble-like regions of space-time, or even scars from a long-vanished cosmic civilization's unimaginable engineering. The truth, as always, is probably simpler, but in the Boötes Void, even simplicity feels alien. These whispers remind us that emptiness is an illusion. Space isn't just the absence of things, it's a canvas where even the faintest brushstrokes tell a story. And in the void's quiet, we might finally hear the universe speaking in a language we're only beginning to understand. In the summer of 1989, a radio telescope scanning the Hercules Corona Borealis region picked up something that shouldn't have been there, a signal pulsing with an unnatural rhythm, like a drumbeat echoing through the cosmos. At first glance, it seemed almost deliberate, modulating in a way that defied the erratic chaos of natural cosmic emissions. The signal's structure was too precise, too organized, sparking whispers of extraterrestrial contact. But as astronomers dug deeper, they uncovered a far stranger culprit, the violent turbulence of interstellar gas clouds, twisting radio waves into patterns that mimicked intelligence. What made the Hercules corona signal so baffling wasn't just its rhythm, but how that rhythm evolved. Unlike the steady pulses of a pulsar or the random crackle of a quasar, this signal's modulation shifted unpredictably, sometimes smooth, sometimes jagged, as if an unseen hand was tuning a celestial radio dial. The key to unraveling the mystery lay in the physics of plasma turbulence. Gas clouds aren't serene, floating veils. They're cosmic whirlpools, churned by magnetic fields and stellar winds until their particles spin into chaotic eddies. When radio waves pass through these maelstroms, they don't just scatter, they're sculpted, stretched and compressed by the cloud's invisible currents. The result, a signal that looks eerily engineered, its modulations tracing the hidden fingerprints of interstellar weather. Modern simulations reveal just how deceptive this process can be. Imagine shouting into a hurricane. Your voice wouldn't just fade. It would fragment, with syllables looping back or vanishing entirely as the wind tore them apart. Gas clouds do the same to radio emissions, but with a twist. Under extreme turbulence, certain frequencies can briefly amplify, creating the illusion of deliberate patterning. The Hercules corona signal's drumbeat might have been nothing more than a cosmic echo chamber, where random waves collided just right to produce fleeting order. Yet skeptics still grapple with one nagging inconsistency. If this was purely natural, why haven't we found more signals like it? The answer might lie in the cloud's unique composition. Surveys later revealed the region was dense with polycyclic aromatic hydrocarbons, complex carbon molecules that can interact with radio waves in ways simpler hydrogen clouds can't. These molecules might act like tiny tuning forks, resonating at specific frequencies and adding another layer of distortion to the signal's journey. Combine that with the cloud's turbulent motion, and you've got a recipe for a once-in-a-lifetime cosmic illusion. The Hercules corona signal's legacy isn't just about a false alarm, it's a masterclass in cosmic mimicry. Gas clouds, once seen as passive backdrops, are now understood as dynamic artists, capable of crafting signals so intricate they blur the line between nature and technology. Every time we point our telescopes at the void, we're not just listening to the universe, we're listening through it, and sometimes the medium speaks louder than the source. Some of the universe's most deceptive signals don't come from advanced technology, they're brewed in the chaotic hearts of gas clouds, where simple molecules like methanol can mimic the precision of an engineered broadcast. Methanol masers, nature's version of cosmic lasers, occur when these clouds amplify specific radio frequencies into strikingly narrow, powerful beams. Unlike the messy static of most cosmic emissions, these flares are so clean and consistent that they've tricked astronomers into double-checking their instruments more than once. The magic happens in star-forming regions where young, violent stars pump energy into surrounding gas clouds. Methanol molecules, jostled by this radiation, begin vibrating in sync, like an orchestra tuning to a single note. When conditions are just right, the molecules release this stored energy as coherent radio waves, creating maser emissions millions of times brighter than what would occur naturally. The result, a signal so sharp it could pass for a deliberate transmission. One particularly infamous example, G22.339 plus 0.060, flared so predictably in the 1990s that researchers briefly entertained the possibility of artificial modulation before tracing it back to a swirling disk of molecules around a newborn star. What makes these masers so convincing isn't just their intensity, it's their persistence. Some methanol flares have been pulsing for decades with clockwork regularity, echoing the kind of stability we'd expect from an alien beacon. The NGC 603-3 region, for instance, hosts a maser that's maintained the same frequency for over 30 years, drifting less than 1 part in a billion. That's more precise than most human-made radio transmitters, yet the explanation is purely natural. The cloud's density and temperature have remained eerily constant, creating ideal conditions for sustained amplification. The real twist comes when these signals interact with other cosmic phenomena. In 2018, a team monitoring the W3OH region caught a methanol maser flickering in sync with X-ray bursts from a nearby neutron star. The star's radiation was essentially pumping the gas cloud like a cosmic switch, turning the maser on and off in a pattern that looked eerily like coded pulses. For a brief moment, researchers wondered if they'd stumbled upon a natural amplifier being hijacked by something else. The truth was almost as strange. The neutron star's magnetic field was channeling particles into the cloud, creating feedback loops that mimicked intentional signaling. Yet the most profound lesson of methanol masers isn't their uncanny resemblance to artificial signals, it's how they reveal the universe's hidden order. These flares emerge from chaos, proving that even in the turbulent depths of gas clouds, nature can produce precision that rivals our best technology. Every time we detect one, we're reminded that the line between the natural and the artificial is thinner than we think, and that the cosmos has been broadcasting its own kind of poetry long before we thought to listen. The cosmic microwave background, the afterglow of the Big Bang, should be almost perfectly uniform, a faint whisper of heat filling every corner of the universe. Yet one patch in the constellation Eridanus defies this rule. Known as the CMB cold spot, this region glows significantly colder than its surroundings, as if something invisible has taken a bite out of the primordial light. For years, astronomers wrestled with explanations, from cosmic defects left over from the universe's birth to the chilling possibility that we're seeing the imprint of a parallel universe brushing against our own. But the most compelling answer might lie in the shadow of a supervoid, an unfathomably vast, nearly empty bubble of space where interstellar gas clouds play the role of cosmic illusionists. Picture a supervoid as a spherical desert stretching over 1.8 billion light-years. Its interior so devoid of galaxies and matter that light passing through loses energy, stretching to longer, colder wavelengths, an effect called the integrated Sachs-Wolf effect. Normally, this wouldn't create a stark temperature drop in the CMB, but if this void isn't entirely empty, if it's threaded with sparse, cold gas clouds, those wisps of matter could amplify the cooling effect like frosted glass diffusing sunlight. The key lies in the cloud's distribution. Unlike the chaotic sprawl of typical interstellar gas, supervoid clouds might form a delicate, web-like structure, their cumulative gravity subtly warping the CMB's photons on their way to Earth. The result, a cold spot that isn't just a cosmic accident, but a fingerprint of the void's hidden architecture. Critics counter that even the largest supervoids we've found shouldn't cast shadows this profound. That's where things get speculative. Some models suggest these clouds could be laced with exotic particles or magnetic fields that magnify their cooling power. Others propose the void isn't just underdense, it's overstretched, a relic of inflationary physics where spacetime itself thinned out like overworked taffy, leaving gas clouds stretched into bizarre, energy-siphoning configurations. The most radical idea, the cold spot might be a texture in space-time, a knot left over from the universe's violent infancy, with gas clouds trapped in its gravitational wake, acting like a cosmic magnifying glass for primordial anomalies. What makes this signal so mesmerizing isn't just the science, it's the scale of the question. If a gas cloud's shadow can linger across 13.8 billion years of cosmic history, what else might we be missing in the faintest whispers of the sky? The CMB cold spot doesn't just challenge our models, it dares us to look deeper, to question whether even the emptiest corners of the universe are truly as quiet as they seem. In the spring of 2001, astronomers caught a signal so bizarre it earned the nickname Aquarius R2D2, not for any sci-fi fanfare, but for its uncanny robotic cadence. Pulsing with mechanical precision every 11.2 seconds, the emission seemed to march across the radio spectrum like a programmed metronome, sparking immediate speculation about artificial origins. The signal's narrowband structure only deepened the intrigue, resembling the kind of focused transmission a civilization might engineer. But the truth, when it finally emerged, revealed a far stranger cosmic ballet, one where the quantum quirks of interstellar gas clouds turned natural chaos into eerie order. The breakthrough came when researchers traced the signal's origin to a turbulent molecular cloud in the Aquarius constellation, a region thick with swirling ammonia and hydrogen cyanide. Under normal conditions, such clouds emit a cacophony of radio noise, their molecules jostling in disarray. But in rare pockets where temperatures plunge near absolute zero and magnetic fields align just right, quantum mechanics takes the wheel. Molecules within the cloud can enter synchronized states, vibrating in unison like a well-rehearsed choir. This coherence, known as quantum phase locking, transforms the cloud's usual static into razor-sharp periodic emissions, nature's version of a precision radio beacon. What makes the R2-D2 signal exceptional isn't just its regularity, but its resilience. Most quantum-coherent phenomena in space flicker out quickly, disrupted by stray photons or collisions. This one persisted for weeks, its rhythm unbroken, as if the cloud had stumbled into a self-sustaining quantum loop. Simulations later showed how the cloud's unique geometry, a twisted, filamentary structure, might have acted like a cosmic feedback circuit, trapping and recycling energy to keep the signal alive. Picture a room of mirrors reflecting a single light beam endlessly. The gas cloud's tangled filaments did much the same for molecular vibrations, amplifying them into the eerie pulses we detected. Yet the signal's most tantalizing quirk was its frequency drift. Unlike human-made transmissions, which hold steady, R2-D2's pulses crept slowly upward in pitch over time. This drift, it turned out, was the smoking gun. As the cloud rotated, its molecules experienced subtle shifts in magnetic and gravitational forces, tweaking their quantum energy states like a cosmic dial being turned. The result was a signal that didn't just repeat, it evolved, its rhythm betraying the cloud's hidden dynamics. The legacy of Aquarius R2-D2 isn't just about solving a puzzle. It's a window into how the universe's smallest rules, quantum mechanics, can scale up to create illusions of design in the vastness of space. Gas clouds, once seen as cosmic wallpaper, are now proving to be dynamic stages where particles dance to quantum tunes we're only beginning to hear. Every time we decode one of these signals, we're reminded the universe doesn't just contain mysteries, it is the mystery playing an endless game of hide and seek with the rules written into its fabric. In 2019, astronomers listening to the Orion Molecular Cloud Complex, a star-forming behemoth over 1,000 light-years away, caught something that shouldn't have been there, a series of delicate, chirping radio pulses, each lasting just milliseconds. Unlike the rough static of most cosmic emissions, these signals rose and fell in pitch like a bird song, a rhythmic pattern that defied easy explanation. The discovery sent researchers scrambling, because if there's one thing space isn't supposed to do, it's chirp. The Orion Complex is no stranger to cosmic drama. Its towering pillars of gas and dust birth stars in violent bursts, rippling with the energy of newborn suns. But these chirps didn't match any known stellar process. The leading theory, collapsing gas pockets, dense knots of molecular hydrogen giving way under their own gravity. As these pockets implode, they could trigger shock waves that vibrate through surrounding magnetic fields, converting kinetic energy into radio waves. Picture a rubber band twanged in slow motion, its vibrations stretched across light years only instead of sound. It's broadcasting a faint, oscillating signal detectable from Earth. What makes these chirps extraordinary is their precision. Most collapsing gas emits chaotic bursts, but these pulses maintained an eerie coherence, their frequencies drifting smoothly up and down. Simulations suggest the cloud's unique magnetic environment might act like a cosmic tuning fork, stabilizing the emissions into clean sweeps. Even stranger, the chirps clustered in specific regions of the cloud, areas where gravitational forces were tearing apart protostellar disks. This coincidence raises a provocative question. Could these signals be the death cries of failed stars, their gas collapsing not into new suns but into oblivion? Yet skeptics point to an alternate culprit, maser amplification. Orion's gas clouds are rich in water and methanol, molecules capable of turning ambient radiation into laser-like beams under the right conditions. If a passing shockwave briefly energized these molecules, the resulting maser could emit chirps as its gain medium flickered in and out of coherence. It's a cosmic strobe effect, with each pulse tracing the lifespan of a fleeting molecular alignment. The most haunting possibility, though, is that we're hearing something entirely new. The signal's brevity and frequency sweeps don't perfectly match any known astrophysical model. Some theorists whisper about quantum turbulence, a hypothetical state where gas clouds under extreme pressure exhibit quantum mechanical effects on macroscopic scales. In this scenario, collapsing pockets might briefly tunnel between energy states, releasing chirps as quantum signatures writ large. It's a fringe idea, but in a universe full of surprises, even the wildest guesses sometimes hit pay dirt. What lingers after the chirps fade is the unsettling realization of how much we still don't hear. Orion's song might be just one verse in a galactic chorus, its melody too subtle for our current instruments to catch. Every time we tune in, the cosmos reminds us the signals we understand are outnumbered by the ones we've yet to imagine. The universe has a habit of throwing curveballs when we least expect them, and few are as perplexing as the so-called black hole echo paradox. Deep in the hearts of active galaxies, supermassive black holes spew jets of plasma at near light speed, creating some of the most energetic environments in existence. But in recent years, radio telescopes have picked up something bizarre. Signals from these jets that seem to echo, repeating themselves minutes or even hours after the initial burst. The strangest part, those echoes don't come from the black holes themselves. They appear to emanate from the swirling gas clouds light years away, as if the cosmos has its own built-in replay system. At the center of this mystery lies a phenomenon called light echoes. Normally, we see these when light from a supernova or flare bounces off nearby dust, creating delayed ghost images. But black hole jets don't play by normal rules. Their plasma beams are so intense they can ionize gas clouds in their path, transforming them into cosmic mirrors. Imagine a flashlight beam hitting a fog bank. Some light passes through, but some scatters back. Now replace the flashlight with a particle beam hotter than a supernova, and the fog with a cloud of magnetized hydrogen. The result, a signal fractures, scattering across the cloud's turbulent interior before pieces of it ricochet toward us at slightly different times. To our telescopes, it looks like the black hole is stuttering. Yet the paradox goes deeper. Some of these echoes don't just repeat, they change. Frequencies shift, intensities waver, and sometimes entire segments of the signal invert, as if the cloud itself is remixing the black hole's output. One leading theory blames Faraday rotation, where magnetic fields in the gas twist radio waves like a cosmic corkscrew. But there's a catch: the degree of distortion doesn't always match the cloud's known magnetic strength. It's as if something inside these clouds, perhaps pockets of exotic plasma or dark matter interactions, is amplifying the effect beyond what standard physics predicts. The most tantalizing echoes come from galaxies like M87, home to the first black hole ever imaged. Here, signals from the jet's base bounce off a gas cloud 50 light-years out, returning to Earth with a 32-day delay. But when researchers compared the original signal to its echo, they found discrepancies, subtle spectral lines that shouldn't exist. One explanation: the cloud isn't just reflecting the signal, it's imprinting its own signature onto it, like a painter adding brushstrokes to a projected image. Gas clouds rich in complex molecules might absorb and re-emit certain frequencies, effectively embedding hidden chemical fingerprints into the echo. Skeptics argue these anomalies could just be artifacts of our instruments, or perhaps signals from multiple jets blending together. But proponents counter that the precision of the delays, often exact multiples of the expected light travel time, points to something far more deliberate. If they're right, we might be seeing a natural form of interstellar signal processing, where gas clouds don't just carry messages, but alter them in ways we're only beginning to decipher. What makes these echoes more than a cosmic curiosity is what they reveal about black holes themselves. Normally, studying a jet structure is like trying to map a tornado from a single photograph. But echoes give us a time-lapse view, showing how the jet's energy evolves as it interacts with its surroundings. Some researchers even propose using these reflections to sonar map the invisible architecture of black hole jets, turning gas clouds into giant interstellar radar dishes. The black hole echo paradox doesn't just challenge our understanding of these cosmic monsters, it blurs the line between destruction and creation. In silencing their own roars, black holes might have handed us the key to hearing them more clearly than ever. And somewhere in those reverberations, the universe is whispering a lesson. Sometimes, to listen deeply, you must first wait for the echo. In 2012, a hush fell over the astronomy community as researchers trained their instruments on the Draco dwarf galaxy, a faint, unassuming speck of stars orbiting the Milky Way. What they found defied all expectations, a radio signal pulsing from its gas-rich halo with an intensity that shouldn't exist in such a quiet corner of the cosmos. Dwarf galaxies like Draco are cosmic afterthoughts, small and dim, with nowhere near the energy to produce such a conspicuous emission. Yet there it was, a persistent radio whisper that turned everything we thought we knew about these galactic minnows upside down. The signal's origin was as puzzling as its presence. Draco's halo, a sprawling cloud of hydrogen gas enveloping the galaxy, showed unusual turbulence, ripples and knots where the gas seemed to churn against invisible forces. Normally, such activity requires energy injections from supernova or active black holes, but Draco had neither. Its star formation had fizzled out billions of years ago, leaving behind a celestial relic with no obvious power source. The leading theory, dark matter might be pulling the strings. Here's where the plot thickens. Certain dark matter particles, if they exist, could collide and annihilate deep within Draco's halo, releasing energy as they vanish. This process would ionize the surrounding hydrogen, essentially turning the gas cloud into a faint radio transmitter. It's a tantalizing idea, one that would make Draco not just a dwarf galaxy, but a gigantic dark matter detector. Yet skeptics point to a quirkier possibility. The signal might not belong to Draco at all. Intervening gas clouds in the Milky Way could be lensing and magnifying a distant quasar's radio emissions, warping them into a false signature that appears to emanate from Draco's halo. The debate hinges on the signal's spectral fingerprint. Dark matter annihilation would produce a smooth, broad emission, while a lensed quasar would likely show narrow, intermittent spikes. Observations so far haven't settled the score, leaving room for both camps to dig in. What's undeniable is how Draco's signal has forced us to reconsider the hidden lives of dwarf galaxies. Once dismissed as cosmic backwaters, they might be bustling with invisible activity, clues to the universe's largest mysteries written in the faintest radio waves. Perhaps the most haunting lesson of the Draco dwarf mystery isn't about dark matter or distant quasars, but about the nature of discovery itself. Sometimes, the universe hides its greatest secrets not in the brilliant centers of galaxies, but in the quiet, overlooked edges where even the faintest signal can rewrite the rules. Deep in the heart of our galaxy, something is screaming into the void, and it might not be the black hole we expected. Sagittarius A, the supermassive monster at the Milky Way center, has long been known to flicker with radio waves. But in recent years, astronomers have caught these emissions doing something downright bizarre, erupting in rapid, repeating bursts that defy the black hole's usual lethargy. The strangest part, these bursts don't always line up with Sagittarius A's own activity. Instead, they seem to dance to the tune of the chaotic gas clouds swirling perilously close to the event horizon clouds that might be warping, amplifying, and even mimicking the black hole's voice. Picture the scene, a maelstrom of molecular gas superheated to millions of degrees, churning in the black hole's gravitational grip. These clouds aren't passive bystanders, they're frenzied participants in a cosmic feedback loop. Every time Sagittarius A belches out a jet of plasma or a ripple of X-rays, the surrounding gas absorbs and re-radiates that energy, sometimes concentrating it into intense, fleeting radio spikes. It's as if the black hole shouts into a cave, and the cave's walls echo back distorted fragments of the original cry. But here's where it gets weirder. Some bursts appear to originate behind the black hole from our perspective, their signals bent around its gravitational well like light through a lens. The result, a cosmic ventriloquist act where the gas clouds seem to throw their voice across light years. The smoking gun lies in the burst's frequency structure. While Sagittarius A's native emissions smear across a wide band, these amplified bursts often show unnatural sharpness, as if filtered through a cosmic colander. That's exactly what you'd expect if intervening gas clouds were acting as resonant cavities, trapping certain frequencies and suppressing others. Recent observations from the Atacama Large Millimeter Array revealed clumps of ionized gas flickering in lockstep with the radio bursts, not just reflecting them but actively reshaping them. In one striking case, a cloud's magnetic field appeared to focus a faint black hole murmur into a piercing shriek, amplifying it 100-fold before releasing it toward Earth. Yet the most tantalizing possibility isn't just about amplification, it's about creation. Some theorists argue these clouds might generate their own bursts through a process called synchrotron maser emission. When gas spiraling toward the black hole collides with counter-rotating streams, it can trigger shock waves that accelerate particles to near light speed. Under the right conditions, these particles might then stimulate coherent radio waves within the cloud itself, essentially turning turbulent gas into a natural radio transmitter. Imagine a lightning storm where every bolt strikes a tuned resonator, broadcasting static as musical notes. The implications stretch far beyond our galaxy. If gas clouds near Sagittarius can twist and enhance its signals, then similar processes could be muddying our observations of black holes everywhere. What we've assumed are the voices of distant monsters might instead be cosmic remixes filtered through the very clouds we thought were silent. It's a humbling realization. Sometimes, to hear the universe clearly, we first need to learn how it lies. Tabby's star refuses to fade into obscurity, and with every new observation, it only deepens the cosmic intrigue. After Kepler's initial discovery of its bizarre dimming events, astronomers expected the mystery to resolve itself. Perhaps a swarm of comets, a dust-shrouded planet, or even the remnants of a catastrophic collision. Yet years of follow-up studies have only compounded the puzzle, especially when later signals from KIC 8462852 defied even the most creative theories. What makes these later anomalies so compelling isn't just their irregularity, it's how interstellar gas clouds might be distorting our view, turning a celestial oddity into an even greater enigma. Take the star's long-term fading trend, for instance. Over the past century, Tabby's star has dimmed by nearly 20%, a decline too gradual for most planetary or stellar explanations. One provocative idea suggests that a vast, uneven gas cloud could be drifting between us and the star, its densest patches subtly filtering starlight over decades. Unlike solid objects like planets or megastructures, gas doesn't cast sharp shadows. It scatters and absorbs light in complex, wavelength-dependent ways. This would explain why the dimming isn't uniform. Observations show blue light dims more than red, a classic fingerprint of fine dust grains or ionized gas particles. If such a cloud exists, it wouldn't just dim the star. It would also refract its light like a funhouse mirror, amplifying certain wavelengths while suppressing others in ways that could mimic artificial structures. Then there's the star's sudden, erratic dips, some lasting days, others mere hours that later telescopes like the James Webb and Hubble have captured. While early theories leaned toward swarms of comets or debris, gas clouds offer a more dynamic alternative. Imagine a turbulent molecular cloud, threaded with magnetic fields and speckled with dense knots of plasma. As these knots drift across our line of sight, their shifting density could create fleeting, lensing effects, briefly magnifying or dimming the star's light in unpredictable ways. Even more intriguing, some models suggest these clouds might harbor microscopic ice or carbon grains that clump together under electrostatic forces, forming transient screens that dissolve almost as quickly as they form. But the plot thickens when we consider Tabby's star's infrared signature, or rather, its surprising lack thereof. If a massive dust cloud or comet swarm were responsible, the star's light should heat that material, causing it to glow faintly in infrared. Yet observations show far less infrared excess than expected, a discrepancy that gas clouds might resolve. Cold, diffuse gas, especially if it's predominantly hydrogen or helium, doesn't radiate much heat. If the intervening cloud is both sparse and vast, it could block visible light while remaining virtually invisible in infrared, like a cosmic mesh too fine to catch the warmth of the star behind it. The wild card in all this, the star's own behavior. Tabby's star is an F-type subgiant, a class known for occasional violent outbursts. If it unleashed a colossal stellar flare or coronal mass ejection centuries ago, the expelled material could still be expanding outward, interacting with surrounding interstellar gas to create a complex, evolving screen. This wouldn't just explain the long-term dimming, it would also account for why newer observations show the dips becoming shallower over time as the ejected material disperses into the void. What makes KIC 8462852 more than just a stellar curiosity is how it forces us to rethink the interplay between stars and the interstellar medium. Gas clouds aren't just passive backdrops, they're dynamic, shape-shifting filters that can warp our perception of the cosmos. Whether Tabby's star's anomalies stem from a local debris field, a rogue interstellar cloud, or something even stranger, one thing is certain: the universe loves a good illusion. And in this case, the greatest trick might be convincing us we're seeing something extraordinary when the truth is simply hiding in plain sight, woven into the faint, drifting tendrils of cosmic gas we're only beginning to understand. The year 2025 could mark the moment interstellar gas clouds deliver their greatest cosmic prank yet, a signal so perfectly engineered in appearance. It ignites a firestorm of debate about whether we've finally found evidence of extraterrestrial intelligence. Imagine this scenario. A radio telescope array in Chile catches a repeating pulse from the direction of the Orion molecular cloud complex, a star-forming region already notorious for its methanol masers and turbulent gas dynamics. At first glance, the transmission seems impossible, a narrowband signal centered at 1420 MHz, the hydrogen line frequency, pulsing in a sequence that mirrors the first 30 prime numbers. The pattern is too precise, too mathematical to dismiss as natural. Headlines explode. Have we intercepted an alien beacon? Then comes the twist. As astronomers race to confirm the finding, they notice something odd about the signal's dispersion measure, the telltale lag between its high and low frequencies. Instead of increasing uniformly as expected for a distant source, the dispersion flickers unpredictably, as if the signal is being refracted through a funhouse mirror of ionized gas. Spectral analysis reveals faint hydroxyl absorption lines, the fingerprint of a dense molecular cloud along the line of sight. Suddenly, a new theory emerges. This isn't a deliberate broadcast at all, but a freakish act of interstellar mimicry. Gas clouds under extreme conditions can behave like cosmic synthesizers. turbulent magnetic fields might twist passing radiation into coherent pulses, while maser activity amplification by stimulated emission could sharpen random noise into artificial-seeming patterns. The prime number sequence, a fluke of turbulence where shock waves in the cloud's plasma create standing waves that resonate at mathematically spaced intervals. It's the universe's version of a monkey randomly typing Shakespeare. Given enough gas clouds and enough time, one of them was bound to produce a signal that looked intentional. But the real curveball comes when the signal starts evolving. Over weeks of observation, its prime number rhythm degrades into Fibonacci-like sequences, then chaotic bursts, as if the cloud itself is learning and unraveling. This, researchers realize, is the smoking gun. Natural processes don't forget their patterns unless the medium generating them is in flux, the culprit. A protostar buried deep within the cloud, its violent stellar winds churning the surrounding gas into ever-changing configurations. Each time the cloud's structure shifts, so does the signal's message, betraying its natural origin. The implications of such an event would ripple far beyond astronomy. It would force us to confront the uncomfortable limits of our search for extraterrestrial intelligence, how easily nature can counterfeit the signatures we associate with technology. Future telescopes, like the Square Kilometre Array, might need to deploy advanced AI filters trained to distinguish true narrowband signals from gas cloud echoes. Meanwhile, astrobiologists would scramble to redefine the thresholds for what constitutes a genuine technosignature, knowing interstellar gas clouds could be lurking in the data, ready to whisper lies in the static. And yet, the 2025 Anomalies' greatest legacy might be philosophical. If a gas cloud can impersonate intelligence so convincingly, how many past signals have we wrongly dismissed as natural? The universe's jokes, it turns out, are layered with meaning. Every false alarm teaches us something new, not just about the cosmos, but about the fragile line between pattern and purpose. In the end, the gas clouds don't just carry signals, they hold up a mirror showing us how desperately we want the static to speak, from the eerie precision of the wow signal to the cryptic whispers of the dark matter hiss. These 25 interstellar enigmas have one thing in common: they all dance in the shadow of cosmic gas clouds. These vast, turbulent formations aren't just backdrops to the universe's grand tapestry. They're active players, twisting starlight into signals that baffle our best telescopes and bending radio waves into patterns that mock our assumptions. Whether amplifying natural processes into artificial seeming bursts or masking their origins behind layers of interstellar static, gas clouds have proven themselves master illusionists, turning the cold depths of space into a stage for cosmic sleight of hand. Consider the paradoxes they've handed us. The same clouds that turned neutron star pulses into Puritan's false alarms mimicking earthly interference also birthed the Aquarius R2D2 signal, where quantum chaos conspired to create eerie mechanical rhythm. They've hidden black hole echoes in their turbulent folds, stretched the primordial glow of the Big Bang into the CMB cold spot, and even conjured prime number sequences from pure astrophysical noise. Each signal is a riddle wrapped in plasma, challenging us to separate nature's creativity from the faintest whisper of something more. Yet for every mystery solved, a dozen deeper questions emerge. Why do some gas clouds amplify signals while others scatter them into oblivion? How can molecular masers mimic alien transmitters with such unsettling precision? And what unseen forces, dark matter, quantum turbulence, or phenomena we've yet to name, might still be lurking in these veils of cosmic dust? The more we learn, the clearer it becomes. Gas clouds aren't just hiding signals. They're teaching us how little we truly understand about the universe's language. So which of these cosmic puzzles captured your imagination? Was it the haunting cadence of the Hercules corona signal, the star that flickered like a dying light bulb, or the void that whispered when it should have stayed silent? Drop your favorites in the comments and keep looking up, Because somewhere out there, drifting between the stars, another gas cloud is already shaping the next great mystery. The universe isn't just speaking, it's daring us to listen more closely. The curtain might be closing on these 25 signals, but the show is far from over. Every unexplained blip, every anomalous pulse is a reminder that discovery isn't just about finding answers. It's about learning how to ask better questions. So stay curious, stay skeptical, and above all, keep wondering what else might be hiding in the static. After all, the cosmos loves a good encore.